Hi everyone, welcome to Mernda Central Science Labs. I'm Marcus.
And I'm Betty.
And we're your
Lab
techs. Okay, today's topic is the changing states of matter. What is matter? Well, matter is everything that surrounds us. And all the things that surround us are made up of tiny, tiny little particles called atoms, which make up even slightly bigger particles called molecules. And all matter can exist basically in three different states. It can exist as a solid, a liquid, or a gas. Alright, so the two things that we're going to be looking at today are water ice and dry ice. Water ice everyone's familiar with, that's a solid, turns into the liquid, turns into the gas. And everyone's familiar with the whistling kettle because the steam or the water vapour is being pushed out through the whistle. The second thing we're going to be looking at is dry ice. Dry ice is called dry ice because at room temperature it doesn't form a liquid. And if you actually then heat it up, and we'll just do that by pouring a little bit of water into it, it goes into the gas phase, which gives you this spooky movie type effect that you get on movies with the mist floating across as the ice turns into carbon dioxide. Alright, so why are the things around us in different states of matter? Some are solid, some are liquid, some are gas at room temperature. It's all got to do with the amount of energy in the particles or the atoms or the molecules that make up those things. And it's got to do with how much they want to stick together, because different atoms have different amount of stickiness or attraction to each other. And it's also got to do with the amount of pressure around it, which is actually helping to push those molecules or atoms together.
If we could shrink ourselves down 1,000,000 times, this is what the molecules or particles of making up solid ice might look like. As the solid warms, the particles gain more energy and start to move about more freely. When they move freely but are still close together, the change of state to a liquid has occurred. As a liquid is warmed, the particles gain even more energy and start to move more vigorously. They now can break away from the other particles, changing the state from a liquid into a gas. As the gas cools, the particles lose energy and move more slowly until they group together, becoming a liquid once more. The particles cool further and start to move more slowly, and eventually they pack more tightly together and become a solid, where the particles barely move at all.
Okay, so now we've seen how the particles behave in a substance when you heat them up and when you cool them down. We'll have a bit of a think about the dry ice and the normal ice. If you actually build models of carbon dioxide, which is the black one there, and water, which is the blue one there, they look pretty much the same sort of thing. The difference between them is that water is quite a sticky molecule. It attracts other water molecules. Carbon dioxide, on the other hand, has very little attraction to other carbon dioxide molecules. Molecules that stick together more actually freeze more easily because they want to go back together. They want to go together. Carbon dioxide, on the other hand, have no attraction to each other, and so it takes a lot of temperature to reduce their movements until they finally stick together. Alright, so today's experiment, we're going to actually be looking at a couple of experiments that help us understand what causes matter to change from solid to liquid to gas, and also what other factors can influence the temperatures at which these things happen. Okay, so the equipment we need for today, we're going to need to have several beakers. One beaker on the hot plate here, which is going to be boiling away, and 3 beakers at different temperatures. We're going to have it at room temperature, 20 degrees, 40 degrees, and 60 degrees. We're going to set of scales for measuring out salt. We've got a beaker to do the measuring in, and we've got thermometers in each of the things to be able to record the temperatures. And like all experiments, we need to have our safety equipment. We should have our lab coat on because we may get things spilling on us, especially hot water. We're going to have a bit of a layer between us and our skin. We're going to have to wear gloves because when you're handling dry ice is at minus 79 degrees. It actually sticks to your fingers and will take your skin off. So you have to be very careful with dry ice. You can handle it in a beaker, but if you try to pick it up, it will stick to your hands and actually cause you quite some damage. Of course, we're going to have safety goggles because if we get a flake of dry ice hitting our eyes, it's going to seriously damage our eyes. Okay, so our 4 beakers are set up now. We have one at room temperature, one at 30 degrees C, one at 40 degrees C, and one at 60 degrees C. So what we're going to do, we're going to take our ice cube, we're going to put it into a beaker and weigh it on the scales, and record the weight that we got. 24.6, so 24.6 for room temperature. To measure the time it takes for each ice cube to melt, we're going to use a stopwatch, so we've got a nice accurate measure of the thing. So we put the ice cube in, and we start the stopwatch and wait for the minute to pass. As soon as the minute's up, we take the ice cube out again. Alright, so after we've got 1 minute exactly, we put the same beaker back on, which was zeroed, and we'll put the ice in, and the weight is now 18.3 grams. So we'll write 18.3 grams in our results table. Going on to the 30 degrees temperature beaker, we put the beaker on the scale and zero it again just to make sure we don't have any residue water in there. We put our ice cube in there and measure its weight, 24.8 grams, so 24.8 grams. We then put it into the 30 degree thing and we'll measure exactly 1 minute and we'll see what the weight is after 1 minute. Take the ice cube out of the 30 degrees thing, put the beaker back on and we'll measure the weight and it's 11.7 grams. So trial at 40 degrees C, put the ice block into the beaker to measure its initial weight. It's 23.9 grams, 23.9 grams. Put it into the 40 degree water and we'll wait exactly 1 minute and see what the weight is at the end of 1 minute. Okay, so again we'll just take our remaining ice cube out of the water, put the beaker on the scales, and we have 6.9 grams. So you can see it's actually melting much faster in the warmer water. Okay, so for our last trial in 60 degrees C water, we'll put the ice cube in and measure its initial weight, and it is 25.2 grams. We'll wait our 1 minute and see how much the ice has vanished. We take the remaining ice cube out of the 60 degree water, put it onto the scales, and what we have now is 2.1 grams. So you can see over the different temperatures, from 15 degrees, 18.3 grams was left, to 11.7, to 6.9, to 2.1. There is a dramatic increase on how quickly the ice melts the warmer the water gets. So it's up to you guys to work out why that's so. Okay, so for the next part of the first experiment, we're going to compare on how temperature affects the dry ice changing from solid to gas, in other words, subliming. To do that, we're going to get a conical flask, we're going to get a beaker on our scales, we'll go for about 20 grams of dry ice. There we go, that's close enough to 20 grams. We'll quickly pour the dry ice into our conical flask, making sure we're wearing gloves. We'll place a balloon over the top of the conical flask and we'll put it into the room temperature water to keep it at the room temperature water. Start our stopwatch and we'll time it for, let's say we'll time it for 30 seconds only, because it will give us a bit more of a quicker experiment and also make it easier to get the differences in sizes. So we've almost got 30 seconds up. Alright, as soon as the time's up, we will take the balloon off, we'll tie the balloon up, and we will label it with the temperature that it was tested at, which is room temperature. So room temperature for the first one, we'll put that sideways so that we can measure it later, and we'll go on to the second one. Alright, so that's about 30 seconds. We'll take the balloon off. Tie the balloon up and label it with the temperature that we tested it at. So, 30 degrees C. Okay, so that's our 30 seconds up. And we'll just tie the balloon off. And we will label it with the temperature, which was 40 degrees C. Place the conical flask into the 60 degree water and we'll time for 30 seconds. We'll tie the balloon off and label it with the temperature. So that's 60 degrees C. Alright, so these are the results of our dry ice at different temperature sublimation test. And as you can see, there's quite a marked difference between the highest temperature at 60 degrees over here and the room temperature, which is about 15 degrees at the other end here. So all we have to do now is to work out the actual difference, or to measure the difference, is to measure how far it is around each balloon, the circumference of each balloon. So we get a tape measure and we measure around each balloon. Go simply around there. The first one is 32.5 centimetres. So we write that down. The final test, which was done at 60 degrees with the dry ice, and if we measure around the balloon, we get 52 centimetres.
These are our results for the effective temperature on the change of state of water ice to a liquid and dry ice to a gas. You could now draw a graph to show how temperature affects the change of state.
We're now going to have a look at how we can actually alter the temperature at which things happen with things like water, for instance. Now, we all know that water boils at about 100 degrees, but it actually can vary up and down depending on where you are. On the top of Mount Everest, it actually boils at 62 degrees, not 100 degrees, as we all know. So what we're going to do, we're going to try alter how sticky the molecules are that hold the water molecules together to change the temperature at which it goes from a liquid to a gas. Now, salt actually makes the water molecules want to group together even more strongly. And if you think about what a liquid is, which is particles that are closer together, if they group together more strongly, it's going to take more energy to make them actually break apart into a gas. So it should, hopefully, increase the temperature at which the water boils. So what we're going to do, we're going to add 5 grams of salt, then 10 grams of salt, then 15 grams of salt, and see how the temperature changes when the water gets back to boiling. Now, if we look at the water at the moment, you'll be able to see the bubbles on the bottom of the thing, so it's gently boiling. So 5 grams of salt, we're going to add it to the thing. Now, if we watch carefully at the bubbles, when we add the salt, what happens to the bubbles? Alright, so for a short while, the bubbles completely disappear, telling you that the water is no longer boiling. So if we looked at our thermometer, to start off with, we had 91 degrees, and it's now going up to 92 degrees, and the water has started to boil again. So there was a 1 degree increase in temperature for the water to boil. Alright, so we'll try the same thing at 10 grams now. There we go, it's 5 grams of salt. We're going to add it to the water and again see if the actual boiling bubbles stop from happening when we add the salt. And again, for a short while, the water stops boiling and the water is starting to boil again. And if we look very carefully at that, in fact, it's gone up to 93 degrees now. Okay, so the water's boiling again after adding 25 grams of salt now. And if we look at the thermometer, we have a temperature of about 96 degrees C.
So these are our final results of how adding salt affects the boiling temperature of water. You could now draw a graph to show how salt changed the boiling temperature.
Alright, so that's the end of our experiment for today, and let's think about what we might have learnt. We've learnt that all things around us are made up of chemicals, which are made up of molecules, which are very tiny particles that move about. In a solid, we know that they are very closely packed, they don't move much. In a liquid, they're a little bit more spaced apart, but still quite close and move about a little bit more. And in a gas, they're widely spaced apart and they move around quite a lot. Now, we also found out from our experiment that the warmer you make ice, the quicker it melts, which kind of makes sense from what we've just said. We also found out that the warmer you make dry ice, which is frozen carbon dioxide, the quicker it sublimes into carbon dioxide gas. From our results, you can draw up some graphs and see what the relationship with the temperature and subliming and melting is like. We also found out that if you add salt to boiling water, it actually increases the temperature at which it boils. And the more salt you add, the higher the temperature gets. We also found out that things like pressure cookers work by increasing the pressure. Pressure holds the particles together more, and it increases the temperature at which the water or the liquid will boil, change from liquid to gas, because the particles are being held together much more strongly by the pressure. So it's up to you guys now to draw some graphs and to write some conclusions for yourself and to think about what you've seen today.
And to finish up today, we will have a look at a few fun things you can do with the changing states of matter.
Alright guys, that's it from Mernda Central Science Labs for now. Bye from me, Marcus.
And bye from me, Betty.